Good morning, students. Today I am going to talk about Mossbauer spectroscopy. This is part 2, and in this section I am going to discuss the various parameters that affect the spectrum. So what you have learned so far, that in case of uh, emitting material and absorbing material, if both are same, that is the nucleus excited, which is in excited states, that emits the gamma ray, and the nucleus which is in ground state, that is what we mean by absorbing nuclei, both are in identical environments, then in that case you are going to get a single line without any shift in the velocity that is plotted on the x-axis. So that is when we have Fe57 as the source and Fe57 metallic iron as the absorber. Both are metallic iron. In that case, you are going to get a single peak without any shift from the 0 0 line on the x-axis, which is the velocity which we write, so that you have already seen in the previous class. So, but suppose the absorber species is different. In that case, there will be slight shift in the positions of the velocity at which resonance occurs. And so what we will find that because uh, the surroundings have changed, the nuclear energy levels also get slightly shifted. So we call this interaction with this surrounding environments of the nucleus interaction with its surrounding environment, and these interactions are called hyperfine interactions. So there is a slight change in the energy level due to this factor, and so transition energy, nuclear transition energy is also changed. So in order to detect this, we need to change the energy of our probing gamma rays, and this is achieved. There are three different ways in which the gamma rays energy the nuclear transition energy is changed, and we do something to change the gamma rays energy, to adjust the gamma rays energy to match those changes obtained as a result of this thing. So these changes due to the hyperfine interactions, the interaction with when the nucleus interacts with the surroundings, such as in the surroundings, there are electrons in the surroundings as well as on the nucleus. At the nucleus also there are electrons. Uh, so these will lead to change. This will affect the nuclear energy levels, and the order of change would be in the on the order of billions of an electron volt. This is a very small change that we are talking about, considering that gamma rays energy are on the order of 10 to the power 4 electron volts. Uh, but this small change in variation in the gamma ray energy, original gamma ray, can be achieved by application of Doppler effect. And so what we do is that we move the source back and forth around a position. The source, the gamma ray emitting source, is moved back and forth, so that that energy and the velocity is per second. So that is, so just like an ambulance, when an ambulance is approaching you, if then there is slight increase in the frequency due to the velocity Doppler effect that we talk about. So similarly here also the source is moving in the forward backward direction in relation to the absorbing species, and so the gamma ray energy will also be altered slightly due to this Doppler effect, and that will be sufficient to match the changes in energy obtained due to hyperfine interactions. So this is what we require an oscillating source, oscillating radioactive source, and make it oscillate back and forth by a few per second, and then we start the recording of our spectrum. So this, if you compare the energy fraction of per second compared to the light, that is 3 to 10 to the power 11 per second, then this small energy shift is which we it is a necessary component to achieve a resonant energy transfer, to the nucleus in the ground state in the absorbing species, which has a different environment. The nuclei have a different environment as compared to the nuclei in the source. So this scale, so for the sake of convenience, so we are basically changing the energy of gamma rays, but for the sake of simplicity, for the sake of convenience, we plot the most typical Mössbauer spectrum is plotted uh, in terms of source velocity as shown in the figure. And this is an example that we were talking about. If you have same environment, if it is this emitter nucleus is metallic iron Fe57, absorbing nucleus is also metallic iron Fe57, then you are going to get only one absorption peak, negative peak like this, corresponding to the zero velocity on the x-axis. So this is what you get uh, if both the nuclei emitting and absorbing nuclei are identical, that is their environment is similar, is exactly the same. There is no change in transition energy, and this is the spectrum is produced. So this is the schematic of Mossbauer setup that we were talking about. This is the plus v velocity, minus v velocity, and this velocity is now you know that mm per second, few mm per second, to account for this hyperfine interactions, the changed energy levels that we have on account of hyperfine interactions, and then you can observe this kind of spectra corresponding to okay, so corresponding to different energy levels. Okay, so with an oscillating source, we can now modulate the energy of the gamma ray in very small increments. We have now good control over the energy of gamma ray. Now the modulated gamma ray energy matches precisely with the energy of a nuclear transition in the absorber, and resonant absorption occurs, and we see a peak. As we see this sample, there's one important point over here regarding the sample preparation, that sample must be thin enough to allow the gamma ray to pass through it without any attenuation. Um, we need to have relatively low energy gamma rays are suitable for this purpose. Uh, the absorption peak, as shown in the previous slide, was at 0 mm per second. So the source and absorber, when the source and absorber nuclei are identical, the energy levels in the absorbing nuclei can be modified by the environment. Suppose if I am placing an iron atom, iron surrounded by cyanide ions, or iron atom surrounded by carbonyls. So, or if I am taking away a few electrons from the periphery surroundings of, I am converting an Fe0 to Fe2 plus. All these changes in the surrounding environments, and this is going to affect your Mössbauer spectrum. So there are three different ways in which this can occur. That is isomer shift, quadrupole splitting, and magnetic splitting. This is a schematic of the source. So how was experiment is carried out. So the gamma ray source moves back and forth, and you have small modulations can be achieved in the gamma ray energy to match for this hyperfine interaction, the changed energy levels for the hyperfine interactions. And so now you can have at different velocities, now you are having the absorption peaks with varying intensities. So due to the hyperfine interactions, you can have where the graph will change, and the events. So basically, you have this was the first example in which the both are identical, the absorbing species and the source, gamma ray source, and then you can have a situation where there is a slight change in the energy level as shown over here. Both the ground state and excited state energy levels are slightly altered, and so therefore you need a slight modulation of the transition gamma ray energy, and so at a certain velocity of this source you will observe resonant absorption, and so the photon counts will decrease, that you see as a dip here. So this is the kind of thing that you will get. Now consider, in addition to that, or if you have something, if there is electric field gradient is present at the nucleus, then you are going to have, and the nucleus has nucleus itself is asymmetric. In that case, you are going to have this kind of splitting that occurs. That we will understand each of these one by one in detail. So this is the quadrupole splitting. This is due to electric field gradient, and then we add another term, that is magnetic field. That magnetic field could be external, could be internal, due to the orbital motion of electrons, due to the spin exchange, or spin polarization, or uh, spin magnetic moment. So all these factors will contribute. So even in the absence of external field, you will have this kind of, if there is net magnetic field acting on the nucleus, there will be a change in the energy levels. In this manner, it will be split into various lines according to their quantum numbers. So all these will be discussed in detail. So first we start with this isomer shift. Isomer shift arises due to the non-zero volume of the nucleus and the electron charge density due to s electron within it. So the s orbitals has the electrons in the s orbital. For s orbitals, there is maximum electron density at the nucleus, and so this if is from one if the species under consideration has different magnetic environment. For example, if you remove 4s electrons, or if you let if there are 4s electrons remain in the on the Fe atom, and that will have lead to a different situation, because so if 4s electrons are removed, then the electron density will decrease. If they remain in the zero valence state, the s electron will be maximum. So that kind of situation will lead to a change in this nuclear environment that we were talking about, non-zero volume of the nucleus and electron charge density. This leads to, so presence of this electron charge density at the nucleus leads to a monopole interaction, Coulomb interaction with the nucleus, which is positively charged, and it will alter the nuclear energy levels. So any difference in the s electron environment that we were talking about earlier, due to the change in the surrounding ligands, there could be oxidation, removal of an electron. So all those things are going to affect this monopole interaction because of the presence of electrons, the s electrons at the nucleus. So this is the primary effect that we obtain. So there will be a shift in the whole spectrum, positive or negative direction velocities, depending on the s electron density, and the centroid of the spectrum will be shifted. As the shift cannot be measured directly, it is quoted related to the known absorber. So we take the reference, our reference as Fe57 as our reference, metallic Fe57. This is what we know as alpha iron, and the isomer shift is useful for determining valency states, ligand bonding states, electron shielding, and electron withdrawing power of electronegative groups. So this isomer shift that we obtain is very useful for determining these things, as stated over here. So for an example, if we can, I can tell you that Fe2 plus or Fe3 plus, one is 3d6 system, another is 3d5 system respectively. Fe2, the ferrous ions have less s electrons at the nucleus, because you have greater number of d electrons in Fe2 plus, 3d electrons, as compared, and there are less d electrons in case of Fe3 plus. So there is greater shielding in case of Fe2 plus, so shielding of the 3s electron, which leads to a decrease in the s electron density in case of ferrous ions at the nucleus. So So greater screening, greater shielding of the by the d electrons leads to decrease in the s electron density. Ferrous, so the ferrous ions will show a larger positive shift, isomer shift, as compared to the ferric ions. So this is how we can relate the velocity of the source velocity with the energy of gamma ray and isomer shift. All three are correlated over here. This is the source velocity, this is the energy of the gamma ray emitted, and this is the isomer shift. So all three are correlated to each other in this manner, and so it is possible to uh, by performing these analysis, it is possible to know the chemical shift values as shown over here. Chemical shift, that is the how the energy levels, nuclear energy levels have been changed. And this is the second part. We will cover it later. That the quadruple splitting occurring due to this factor. This is additional factor that comes in due to the electric field at the gradient at the nucleus. So moving ahead. Okay, so one moment, please. So what we know now, there is some technical problem. I have just a moment. So this isomer shift is also called the chemical shift sometimes, because it is due to the change in chemical bonding environment, chemical bonding situations. It gives it gives rise to such shifts, and so we can okay. So this chemical shift is can be stated. It is given by this equation. So what you see here is that the isomer shift del is 4 pi phi is equal to this minus pi z e square. So usual, whatever the meaning that you attribute to these symbols, it is the same thing. Z is the nuclear number of protons in the nucleus, and E is the electronic charge, and this R here is the radius of the nucleus, and del R by R is the change in the radii as when we are comparing this excited state nucleus, nucleus in the excited state, nucleus in the ground state. That change is given by del R. So excited minus ground state. So the radius change is del R. And this superscript here, this term that you are seeing over here, size square, that's electronic wave function, s electrons, and at distance. So we are only considering the radial part of the electronic wave function. So when r is equal to 0, the small r value, the radius is 0, so that what symbolizes, the 0 symbolizes over here. And this A is meant for the absorbing species. And similarly, this is the electron density at the nucleus at r is equal to 0 in case of the source, nucleus. So the shift of nuclear energy levels is caused by an electrostatic interaction between the positively charged nucleus and the negative electronic charge. So it is called, so we call it isomer shift because the difference in the nuclei radii del R of the ground state and the isomeric excited state. So it will depend on this difference in the nuclear radii of the excited state and the ground state, which can be said taken as an isomer of each other. So few important points about this equation, about this electron density thing. So you can see that for Mössbauer nuclei which have a smaller radius in the excited state, so there are different situations we are talking about this second term. So there are two terms that we are considering over here. One is the electron density at the nucleus, change in electron density with respect to the source, and change in the absorber nuclei with respect to the source. And the second thing is the change in the radii, change in the radius of the nucleus in the excited state with respect to the nucleus in the ground state. So there can be two cases. There are some cases in which the excited state has smaller radius. Iron is an example of that, Fe57. So in the cases where you have smaller radius of the excited state than in compared to the ground state, as happens in the isomer shift del decreases with increasing electron density. So that is quite obvious. If this is negative, this and the electron density increases in this absorbing species, so this whole term becomes the bracket terms become positive. Positive into negative gives you a negative thing, a negative value overall. So del the isomer shift will decrease with increasing electron density in such cases, and vice versa is also true. If this if this is in the absorbing species, the electron density decreases at the nucleus, then that will lead to a positive isomer shift, that is an increase in the isomer shift, you can say. There are also cases where the nucleus in excited state will have a larger radius. Such an example is the tin 119. In this case, you can imagine if this term becomes positive, so increase in the electron density in the absorbing species will lead to overall increase in the isomer shift. So that's quite obvious considering the equation. You can also simplify this equation as and you can have for a given nucleus, this this term as well as this term becomes constant, and the two variables would be this absorbing species, electron density. Even this term would be also, if I say that I am only going to discuss Fe57, then this term is constant. The decrease in the nucleus radius of the nucleus. The only variation would be due to this factor, change in the s electron density of at the nucleus. So ferrous ions have larger positive isomer shifts than ferric ions because s electron density at the nucleus of ferrous ions is less due to greater screening effect of d electrons. So this is what we have already discussed earlier also. So this psi s0 square should not be confused with the number of s electrons in the atomic number. So now you have to visualize this psi is the wave function. You have to visualize the electrons as waves. And if you are visualizing, so in that sense you don't count in the numbers, you talk in terms of the amplitude of the wave and the electron density due to the electron as a wave, so square of the amplitude. So that is how you have to visualize the thing. Otherwise, in terms of numbers, if you do it, it will be confusing. It won't work. So you have to start visualizing the electrons as waves if you are not already doing it that way. So it is this s electron density at the nucleus, and as such will be affected not only by the s electron population but also by the screening effect. So if you are having a wave which is having trouble you are obstructing it some way path, or if you are visualizing the electrons in which are in outer shells but they are not able to see the full charge at the nucleus, that because of the presence of inner shell electrons which act as a shield. So that shielding due to the inner shell electrons, and even the electrons within the same shell will also contribute to shielding, but to a lesser extent, but they will definitely do. So we will see that the 3s electrons are also shielded by d and f electrons. 3s electrons also shielded by 3d electrons, that we will see in this case also. So, but that effect compared to the inner shell, second shell or first shell electrons shielding, the shielding effect would be greater. For 3s will be better shielded by 1s and 2s electrons than as compared to other electrons in the third shell, but there will be effect, and this is crucial. We will this gives us very crucial information about the bonding when we consider this shielding by d electrons within the shell. So electrons in the 1s, 2s, 3s, all the shells contribute to psi s 0 square as shown over here. The electron s electron density. This is the s electron density at the nucleus that we are talking about. But as the quantum number increases, the contribution to the electron density at the nucleus will decrease gradually, 1s, 2s, 3s, 4s. So for those obvious reasons, if you consider the nuclear amplitude of a wave, you will see that 1s electron has the maximum the amplitude is much greater as compared to 2s. All of them will have a high amplitude at the nucleus, maximum amplitude at the nucleus in their wave profile, but 1s electrons will have even greater amplitude than 2s, and 2s will have a greater amplitude than 3s, and so on at the nucleus. So the inner shells are not so when you are considering the effect of bonding, the inner shells, like if you have, so for example we are considering here iron as an example. So third shell is our valence shell. So first and second shell electrons, the s electron density won't be that much affected when the bonding, when we are considering in case of different bonding situations. But the 3s and 4s, third shell 3s and 4s electrons will be affected to a great extent, and that is the crucial thing. By using this kind of nuclear transition, we extract the information about the valence situation about around the bonding situation in a molecule or atom. So shielding by other electrons effectively increases the s radial wave function. When you have shielding in terms of wave, if you are looking at the wave profile, the shielding has an effect of increasing the radial wave functions, and decrease, so that we say that the radial wave function undergoes an expansion and decrease in the s electron density, and there is a decrease in the s electron density at the nucleus. So so if you can see here, 3d6 4s1, 3d7 4s1, there are two configurations we can compare. So 7d is 7d electrons over here, 6d electrons over here. In the outer shell, in the fourth shell, there is one electron, so that's okay. These d electrons will shield the nuclear charge, and this electron in the s orbital is not able to see the full nuclear charge at the nucleus. It will feel only partial attractive force, which only a partial force of the nucleus, attractive force, that will be seen by here. Similarly here also they will be shielding, but the extent of shielding will be different, because the number of d electrons are more, there will be greater shielding. So the s electrons will not be able to feel the full force, even lesser force of the, they will feel even lesser force of the nucleus. So this is what we were calling shielding, which arises due to repulsion of the inner core electrons, mainly due to inner core repulsion. But as I said, even the valence shell electrons will also contribute to the shielding, but to a much less extent. So this is an example where we are 3d d electrons are inner part of an inner shell, and they are shielding the outer shell electrons, such as 4s1 here. This the second example is of the d electrons. 3D, so you have 3d5 and here 3d6. So these 3s electrons are present at the nucleus. They also present and the wave function decays to 0 only at the infinity, so they have also a presence elsewhere away, far away from the nucleus also they have their presence. So the 3d electrons, the number of, as the number of 3d electrons increases 5 to 6, there will be greater shielding of 3s electrons, and the s electron density in this case sorry, in the second case, where number of d electrons increase, the 3s electron density contribution at the nucleus for the 3s will decrease. It will be decreased because of that. Okay, so because 3d orbitals are also able to penetrate the 3s wave functions. So the two, and because of that interaction, 3s electrons will be shielded. So you must, here what I am trying to emphasize, that you must brush up your concepts of shielding and penetration, which you learnt in the first semester of BSc honors. Most of you have studied. I teach these concepts in shielding and penetration with respect to the wave functions in the BSc first semester. You must be, so most of you I know will not be aware of this shielding and penetration. So I'm just going giving a brief overview of these things. You must understand the radial part of the electronic wave function. Thus, when we consider electrons as standing wave, remember standing wave. Electrons in an electron behave as standing wave, not like a traveling wave. So when you have to qualify that part, wave, standing wave. Okay, so this is that can be split you from your earlier knowledge of quantum mechanics and earlier classes, on even in inorganic chemistry we teach students about this, that the wave function, electronic wave function psi, has two parts. One is radial part and angular part. So if we consider, let us consider the radial part here. So this is 1s, n is equal to 1, L is equal to 0, 1s wave function. This is the radial wave function for 2s, R to 0. So look at this S, 1s, 2s and 3s wave functions. So what do you think when this small r is 0? So all of them have exponential profile, that is a decay, exponential decay profile is there. And so when r is equal to this whole term becomes 1, equal to 1, and this is the maximum value that you can achieve, 2z by 3 by 2. So this will be the maximum. For any other increase in r, the value is only go on decreasing and becomes 0 when r becomes infinity. So this is a typical exponential decay profile you will obtain. This exponential decay profile is common to all the orbitals that you see here, but there is and if you substitute r is equal to 0, r is equal to 0 here, you again, even in case of 2s, you will get a maximum value of the function. A maximum value of the function can be achieved when you substitute r is equal to 0 here, here, here. Similarly, go to the 3s wave function. If you consider this, when you substitute r is equal to 0, this function becomes 1, this is 0, this is 0, and so this whole thing is having a maximum value. So we can say that the amplitude of the wave, electron wave, 3s electron, 1s electron, 2s electron, have maximum amplitude at the nucleus when r is equal to, small r is equal to 0. Okay, so let's try to draw it out. So what you so this capital R is the wave function, radial wave function, and when you square it, you get the electron density, and then you multiply it by 4 pi r square dr, the thin shell volume of the thin shell around nucleus. Then you get the, so you get this radial electron density. Here you get the radial probability function. So this is you must understand. So I hope you understand all these things. I need not go into details of all these things. because this is earlier you have studied this in your quantum mechanics classes. So this is very important for us in this context. The context in which we are discussing this electron density term is very, very important, and this is what is giving you a value, a maximum, the values of electron density at the nucleus. So electron density at the nucleus is quantified by this squaring this wave function. So and then this is another term which you more commonly refer to as radial probability function. This is simply this electron density term, electron density multiplied by the volume of the thin shell, at a distance r, which has a infinitesimal small thickness dr. So this is how we define electron density into volume, you get a probability function which you normally know. So these are the points that you must know, and so we will focus on this part, this density at the nucleus, r is equal to 0. So this is, so considering the 1s profile, so the function that I showed you in previous slide, I'm just trying to follow it up with the curves, how the plot will look like. So this is the r is equal to 0, we are at the nucleus, and we have maximum amplitude of the wave, and it decays like this, it goes like this, decaying, and becomes 0 at the infinity. So now when you square it, the values that you show at the nucleus, amplitude ka square, if we do it, square this function, whatever value we have, it should be double. So 2 square of 2 is 4, so we are getting 4 over here. So this is the amplitude which is being plotted over here, and then we have this 4 pi multiplied by 4 pi r square terms. This gives us the probability. So we are having maximum amplitude here, and when you square it, you get it the maximum electron density. It is at the nucleus. This is at the nucleus. So one s electron has maximum electron density at the nucleus. Similarly, 2s electron, it has maximum electron density at the nucleus. So maximum amplitude of the wave, maximum electron density, and you have maximum radial probability. That this is slightly shifted over here. So this is how you analyze the waves, the electrons as waves and their radial parts, which tells you that except for all other orbitals, so for all p, d, and f orbitals, the electron density is 0 at the nucleus. But for s electrons, the electron density is maximum at the nucleus. And this plays a critical role in this our analysis of Mössbauer spectrum. So this most probable radius is this, where you have in the thin shell the maximum probability is there. And the distance at which you have maximum probability of electrons being found out in the thin shell around nucleus. So in contrast, if you view the 2p orbital, typically the wave function goes to 0 at the nucleus. No electron density of p electrons at the nucleus. So if you square it, if you square this function, it will still be 0. So you have 0 electron density at the nucleus. Okay, and then you consider this thing. This is the probability part. We are not interested at the moment in this thing. So maximum amplitude, maximum electron density. So see the contrast. This is just to show the contrast that maximum electron density is not at the nucleus in case of p electrons. And so that's why primarily the direct effect of electronic distribution will be due to which will affect the nuclear energy transitions. Nuclear transitions energy will be due to the s electrons. And although these p electrons and d electrons do not have electron densities at the nucleus, they will have indirect effect in the sense that they can act as a shield. They can shield the nuclear charge for the s electrons and the s electron will not be able to feel the full force of the nucleus, and due to which they will be change in the s electron density. Um, it will not be approaching the nucleus so strongly as in absence of these uh, electrons, 2p or d electrons, etc. So this is a summary of all the three 1s, 2s, and 2p. So maximum amplitude, maximum electron density, maximum probability, maximum amplitude for the 2s, maximum amplitude, so these two things you must be very clear about. This is what we are is going to be relevant for our discussions in Mössbauer spectroscopy. Maximum electron density at the nucleus, R is equal to 0. So these are the profiles which will be interesting for you. And 2p, this is a summary of all the previous discussion. And similarly, you can also plot 3s, 3p, and 3d orbitals. And so this is we have maximum amplitude of 3s at the nucleus, 3p and 3d. You can see. So again, so here there is an important thing that 3d electrons will also affect the wave function of when they are present. If the number of d electrons increases, they have where you are considering they are going to affect this 3s electron waves. So as because of the interpenetration of these wave functions from this wave function into this wave function will lead to slight reduction in the they will affect the wave function, the amplitude of the wave function, and you will have reduced electron density because of the shielding caused by 3d electrons. So, and this is what we are going to discuss in a number of cases in this such transition metals, particularly in iron. This will be the effect which will be which we will feel in every point is very relevant. So this is R square plots. I have not plotted the radial square of the wave function, that you can do it yourself. So these are the most probable radii of the 3s, 3p, 3d respectively. And these are you also have subnodal maxima, and these are the thing that you will have find important in case of penetration and shielding. These are the points subnodal maxima play an important role. And so it is not possible to discuss the entire shielding and penetration in this class because we have to keep the focus on Mossbauer spectroscopy. But if you want, you have to revise these things. Read the books by Inorganic Chemistry by Hui or Shiver and Atkins. You will find this penetration and shielding thing. So we come back to so now you have understood the radial part of the wave functions. So we can continue our discussion on the isomer shift in relation to that. So you have a nuclear source nucleus. This is absorber nucleus. A source nucleus is in the excited state. So as I said, in case of iron, the excited state has smaller size. So that's what is depicted over here. And this is the absorber nucleus is in ground state. It has a bigger size. That's why it is larger, shown over here in this manner. This excited state nucleus in the source emits gamma ray, which will be absorbed by this nucleus in the ground state. Okay, and this is what nuclear radius I just discussed. Electron density is rho s in the source, rho a in the absorber at the nucleus, electron density at the nucleus. And so 1s, 2s, 3s, 4s, these are will have direct effect on the nucleus electron density. So the electron density will be affected directly by the change of electron population in s orbitals, mainly valence s orbitals, 3s, 4s, and they will have direct effect on this. Indirectly, the p, d or f electrons will also contribute because, as I discussed, they can increase or decrease the shielding. So when you take away one electron from d orbital, the shielding is decreased. When you add electrons to the d orbital, the shielding of 3s and 4s increases. and so there will be so that will lead to increase, so that will have the change of the s electron cloud at the nucleus, and which will lead to a different type of, so this is the indirect effect on the s electron density. Typically calculations is shown over here for 1s with variation in the electronic configuration 3d8, 3d7, 3d6, 3d5, 3d6 for s2. So this is the free atom Fe0, 0 valence state, Fe3 plus, Fe2 plus, Fe plus, and this is the situation. So Fe plus has three, Fe1 in oxidation state has 3d7 configuration, 3d6, 3d5, and so on. So as the number of electrons in the d orbital increases, you can see number of electrons with increase in d electrons 5, the s electron density is getting is affected, it decreases. Because why? Because these d electrons are causing a shielding. They are acting as a shield for the nucleus. The distribution of d electrons around the nucleus is having an effect of a shield, and the positive charge is not felt as strongly by the s3s electrons as in a free atom it would have been. So so you can clearly see that 69, 68, 67, 67.7, 67.5. So there is gradual change in the 3s electron density, whereas the 1s and 2s electron density is not much affected. They are remaining almost the same, constant, but 3s electron density is very seriously affected, severely affected. So this is the direct effect that you are, indirect effect you are seeing due to the change in s electron density due to the shielding effect of the d electrons. Another effect, so here we have considered isolated electrons. In this example we have considered atoms. If we have isolated atoms, this is the situation, Fe3 plus, Fe2 plus, Fe plus. But in case of a coordination compound, you will have these atoms would be bound to certain ligands. So there will be some covalent bonding also, and that will also further lead to changes in this pattern, the s electron density. So chemical bonds between metal ion ligand, as we now know occurs in coordination compound, will alter this valence as shown in the previous slide, because there will be sigma donation of s electrons from the ligands into the s orbitals of metals, and there will be in some cases there will be also back donation of electrons through pi bonding, d pi p pi bonding. So that will take away electrons from the d orbitals of the metal to empty pi orbital of the ligand. So this will so the shielding will have so this will have direct effect of increasing the s electrons sigma donation from ligand to metal. So increasing, it will increase the s electron density at the nucleus. In case of d pi p pi back donation, the sum of the d electrons are taken away from the Fe site. That means the shielding will decrease. This will also, so what will happen if shielding decreases? This will also lead to an increase in the s electron density. So both bonding mechanism influence the isomer shift in the same direction that we just discussed, but not to different. But the extent of will be different because sigma donation, a sigma bond is stronger, so there will be greater effect in this case. Pi bonding is due to the lateral overlap, so this will have slightly weaker effect. So the statistical weight, if you consider in terms of increasing the s electron density at the nucleus, will be different depending on the metal and the participating ligand. So this is the reason why we so for this reason we obtain a different isomer shift values even for if you consider one oxidation Fe2, you will get different Fe2 oxidation state. 2 plus oxidation state will give you different isomer shift for Fe when it is bonded with water molecules, FeH2O6, and there will be different isomer shift for FeCN6, that is in, both in the +2 state, but because of different bonding situation and depending on sigma donation pi and d pi p pi back donation, there will be different isomer shift for the same oxidations in the same oxidation state. So this is what we see, electron density profile again with in relation to the bonding situations. So here you have on the this side we have electrons in the Fe2 plus state, Fe2 plus, Fe3 plus, and so on. And on this side we have Fe in zero valent state, like here we have Fe in negative ferricyanide. So we have different oxidation states, and different we have different oxidation states. We have different bonding situations for iron in this entire thing, and we can see that there's the in all these things we in the entire overall, if we view it, we can see that 1s and 2s, this is remaining unaffected, but 3s is being affected with change in the bonding situations, and 4s is even the 4s electron density is the most severely affected over here that we see because of the change in 3D electrons and their participation in bonding. So on going from the table, we notice three things that can be noticed in this that we have shown in previous slide. One electron configuration to another. When you go from that, the electron density at the nucleus that originate from 1s, 2s, and 3s contributions is remaining constant, and they are also much higher values, 1s, 2s. They are remain unaffected. So we see that 3s shells, the variation will, so if you are considering the change in electron density, so the effect is 3s is being affected more. So the removal of 3D electrons, oxidation of an iron compound leads to an increase of electron density due to decreased shielding of 3s electrons from nuclear charge. And if you add 4s electrons, example going from Fe2 plus to metallic iron, this will cause electron density, increase the electron density at the nucleus. So this is what we had discussed. We have already discussed how the bonding situation, depending on the bonding situations, for example, in the same oxidation state, will alter the isomer shift. So for one oxidation state, we can have a range of isomer shift values. For example, this is the Fe2 part that we were discussing. We can have, for example, if we consider ferrocyanide FeCN6, which is +2 oxidation state, FeH2O6, which is also in +2 oxidation state, we have different bonding situation. The d pi p pi bonding situation is different, sigma donation is different, and we also have the spin conditions are also different, which can be low spin, high spin, those variations are there. So in all, because of all such cases, you have huge variation in this isomer shift values, ranging from negative values here to positive value for S is equal to 0, that is a low spin state. And similarly, if you go to high spin change, then this has high spin one also have higher positive isomer shift over here. So there is one more thing that will be considered later in next class when we discuss some examples application of this, will be that there will be also be change in the ligand metal to ligand bond length because of the high spin, low spin state and the conditions, and this indirectly will also affect the isomer shift values. So that's why we are having this kind of different Fe3. You have different spin state, different bonding situation. You can have variations, and then so you fix the spin state and change the ligand. You can get the variation from this to this. So we are seeing one more thing that we can see here. Fe1 has the we are getting the highest most negative shift in the isomer shift is obtained in case of Fe6. Most positive isomer shift is obtained in case of Fe1. Why? Any idea? So you will always remember in these discussions that we have the isomer shift is basically while discussing isomer shift, we consider the electron density in the absorber as in reference to the electron density in the source nucleus, and this delta R by R. So this particular thing is going to be constant and it is negative for iron. So the factors that lead to an increase in the s electron density at the nucleus in absorbing species will cause, and so if this factor increases, electron density at the nucleus increases, you have the isomer shift will become negative. So considering these points, if you apply and in case of Fe1, you have a D7 configuration is there, and so the shielding is maximum. So there is a greater decrease in the so the greatest decrease in the electron density is achieved is in case of Fe1 because of the maximum number of d electrons. D7 configuration is there, and so so there is this whole term is negative, is the most negative in amongst all these values, and so negative multiplied by this negative term gives you a maximum positive term in terms of isomer shift. Similarly, if we consider Fe6, it has a D2 configuration, and so this is so least shielding is achieved in this case. So the electron density increases. So this is a positive. This psi s square a absorbing species minus this is a positive term, and maximum positive value will be obtained for Fe6, and so you have so overall this del will be most negative in this case Fe6. So I think I'll stop here, and we will discuss the quadrupole splitting and magnetic field splitting, and due to the magnetic field splitting we will discuss in the next class. We need we will have detailed discussion on these two in the next class. That's all for today. Bye for now.